Right. So I'm Evgeny. I'm co-founder of Fluence. Great to meet everyone who I haven't met yet. So we have here several members of Fluence team, of Fluence Labs team. Dmitry, my co-founder, who's the CTO, who will be doing probably hard work presented today. Tom Trowbridge, also co-founder of Fluence. And all the great guys, Fluence team, Anna, Alexei, Bernard, Valery, Alexei, like you see them all here. So anyway, we'll get some time to talk. So I wanted to remind quickly that what we do at Fluence is a peer-to-peer application platform, or the decentralized cloud, or the peer-to-peer computing protocol. All of that is kind of synonyms. It's basically the development stack and the protocol and the network that allows you to create, deploy, and run peer-to-peer applications. And we have like very specific and great development stack that allow you to do it. We have Aqua programming language that is very special, which allows to create all kinds of peer-to-peer workflows, applications, distributed systems at high level of abstraction without a lot of complexity that you typically have when building peer-to-peer. Fluence is like, we kind of like trying to make Fluence compute layer for the Web3, because in the Web3 we have storage, identity, oracles, like all kinds of stuff, on-chain compute that works sometimes great, sometimes not. But what we miss is really like off-chain complementary layer that would host all like the software, middleware APIs and so on and so forth that cannot go to on-chain just economically, and in terms of just that doesn't make sense to put on-chain, but also you don't want to have it off-chain in centralized cloud. So Fluence is something that replaces centralized clouds and centralized backends. And Fluence stack is very compatible. It's compatible with like any Web3 protocols. Designed the way that you can plug any storage identity, on-chain data, and so on and so forth, like on-chain applications. Yeah, so and it allows you to build a lot of cool stuff. We have like some project, like the network is live already. Basically, the protocol is live. You can try it, you can build it, the development stack works. And we have some projects already building on us. We sponsor hackathons, mainly in the like related to IPFS ecosystem and Ethereum ecosystem, because Fluence is already integrated with IPFS and Ethereum. So like maybe later we can share some details on the bounties that now live. And there will be very cool monetization opportunities. Like the network is open source. It's a peer-to-peer network, open source, but we're gonna have a governance token. We're gonna have the incentive layer for the nodes to perform computations. And we're going to have the ability for developers who create useful components for the network to earn revenue which will be the part of kind of cloud revenue of the nodes. So it's basically the Fluence decentralized cloud is the first cloud that allows you to, as a developer, to get a share of the cloud if your open source component was popular and is being run by other people, which is not possible with existing clouds. Yep. I guess that's it. That's quick intro. Like, I mean, I don't know, like if Tom, you want to add something, you can do it. If not, let's.
No, let's get it going to the tech. Not much to add to what Evgeny said there. The only thing I'd add, actually, one thing is that the community is super important, as Evgeny mentioned, and so really wanted to make this a weekly event and just open it up to the community. So we want to kind of start formalizing that. And if anybody is interested in engaging more with Fluence as ambassador or anything else, please reach out to us, because we want to kind of really be as open and involved with as many of you as we can.
Right, Dmitry, you wanna go with real content? What should they?
Yeah. Let me share my presentation. Okay, can you see the slide? Cool. So my name is Dmitry. I'm one of the co-founders of Fluence. And today I want to briefly introduce Fluence in depth, briefly and in depth at the same time. So I'm not going to tell too much about how the things works. The main purpose is to describe what exists and how everything is related to each other, because we have many moving parts in Fluence. And I will provide, at least I'll try to provide some links where you can read and learn more about parts of the Fluence. So first of all, Fluence is a peer-to-peer network. It's not a blockchain. It's not a kind of network. It consists of peers which are connected together with libp2p. These peers are programmable with Aqua. So this is the entry point into the Fluence network, the peers and their behavior. We have different kinds of peers. Peers could be publicly accessible or not. And we have two implementations of Fluence peers, which have a lot of things and behaviors in common and some different. So let's begin with the common things about the Fluence peer, and let's introduce Aqua. So Fluence peer can be thought of as like a cake with 3 layers. The top layer is connection pool. Not very interesting because libp2p does its job well. It just connects and transmits data. The data in the Fluence network is like smart packages, which we call particles. A particle is both code and data. And this code explains distributed behaviors of the network. So we have this flow. Can you see my cursor pointer?
Yep.
Cool. So we have incoming particles. They are received by the connection pool. Then the particle, the code, and the data is dispatched to the Aqua virtual machine pool. These Aqua virtual machines call services for computations, and then everything goes back. The responses go to the AquaVM. AquaVM says that you need or not send more particles to other peers. So that's very briefly. And now let's discuss what happens there. The main part, the heart of the system of the Fluence network is Aqua virtual machine. It coordinates the travel of a particle from peer to peer. Particle consists of some code in the form of air, I will tell about it later, and data that holds the results of previous execution. So every time the data comes into the air interpreter, into AquaVM, it verifies previous executions, including signatures, data, and so on, that the right peers did the right job. So it's pretty secure. And it finds the next instructions to execute and executes it locally. Then it returns the next steps, what services to call and where to forward the particle after the local processing. For each particle, code execution is idempotent and data is conflict-free. So essentially, every particle forms a single-use coordination network, and it's pretty flexible and powerful. Yep, I'm not sure if you can see the link in the top right, in the bottom right corner, but there is a link. And it exists on almost every slide. You can get more information about everything on this link. It will be on the recording, and I will share the slides as PDF at the very end. AquaVM runs Aqua Intermediary representation. It's the internal representation of the code that's made, that's a low level. It's made for machines, and it gets interpreted on AquaVM. Usually people have no need to see this, but that's what it looks like. It's based on process calculus, so it's a very dense and strict set of instructions, like I guess 9 or so, with very strict rules for execution. For people, we have Aqua. Aqua is a high-level programming language for distributed systems and peer-to-peer. It's a kind of a DSL that lives on its own. It has its own compiler, and it's designed to describe distributed flows, peer-to-peer flows. So that's a snippet of what Aqua could look like. Here we have the fanout event. That's the code snippet from one of the users of the language. And finally, it's compiled to AIR. We have the Aqua compiler. It's called Aqua Fluence Lab/Aqua, and it provides a lot of tooling to organize complex code for peer-to-peer subprotocols, composable subprotocols. So we have type checking with structural typing. The code can be divided into modules, and you can think of and you can provide a distributed algorithm as a library. That's pretty new approach, as you can, for example, make a publisher subscriber or many implementations of publisher subscriber protocols and run them in parallel on the same nodes without need to redeploy them. Or you can implement Kademlia, or you can implement Raft in Aqua, and then add more and more behaviors into it. The compiler targets mainly TypeScript and JavaScript, and the compiler itself is compiled to JavaScript, and NPM is the default distribution mechanism for the compiler and for the Aqua code. So you can find the compiler on the Fluence Labs organization/Aqua on NPM and try it out. Here's some example of CLI usage. And you can try it. We have Aqua Playground, and you can run Aqua in browser even without installing anything. To try it out in browser, open fluence.dev/browser. So that's about all the peers. They are managed by Aqua. They all have a Aqua virtual machine that interprets and verifies Aqua code. And finally, it runs services in some form. The form differs for TypeScript and Rust. So now let's speak about the Fluence Peer implementation in TypeScript. So what is special in the Fluence Peer implementation in TypeScript? First of all, it's the main compilation target for Aqua. So the usual flow for developing for Fluence is to write some Aqua code, then compile it with a compiler with a CLI, and then call it as a TypeScript or a JavaScript function. Here's the example. Get price is an implementation of an Oracle on Fluence. And it's just provided as an asynchronous function for TypeScript. Just call it with await, provide arguments, and that's all. As a JavaScript peer or TypeScript peer is usually running in the web browser, it participates in the network through a relay. So you can deliver the message, deliver the particle to the web browser, or you can participate in the network from the web browser if some fully connected peers are helping you. The services in the TypeScript implementation of the Fluence Peer are implemented as objects. So we don't have it in this example, but the service is compiled to a TypeScript class definition, and then you just call new, implement functions as async functions, and that's it. And the Aqua virtual machine itself is compiled to WebAssembly, and it runs inside the web browser or Node.js or any other client as a WebAssembly module. Here's the link to the repository. It's Fluence.js in the Fluence Labs organization. A couple of words about relaying in Aqua. There is no special protocol for relaying in Fluence. It's just handled by Aqua. And that's what it looks like. You just say that you want to call some function somewhere via relay optionally, and you execute the code there, and that's all. Now let's speak about the Fluence Peer implemented in Rust, also known as the Fluence Node. So the Fluence Peer, the Fluence Node implementation, the full node, fully connected node, its main difference is that it has a Marine, a general purpose WebAssembly interface types runtime to run services. Services on the Fluence Node are compiled to WebAssembly, and therefore they're sandboxed. The modules are reusable. Every service may consist of many modules which could be linked, so they may depend on each other and use capabilities of each other. And this linking capability enables managing effects as modules. So you can isolate some external effect as a module, audit it, ensure that it's secure for you as a node provider, and provide any external data or anything through this module, which is reusable for other services. So you can call APIs, or you can run a microservice, or you can access, for example, IPFS data and more, and encapsulate it into the effector service, effector module. Modules and services on the Fluence node may exchange files, and they have access, isolated, sandboxed, and so on, access to the file system. Where could it help? For example, you can distribute WebAssembly files with code with the help of IPFS and call CID addressed functions. So you can implement function addressability with the help of particle file vault. Or you can plug in another storage. Or you can simply store data on the hard drive and reuse any WebAssembly compiled modules to perform file processing. Or you can, for example, enable database backups, backup data from the database to the disk, and then recover it on another peer or on the same peer if you want to migrate the service, for example, when the version is changed. So it's also implemented. And a couple more words about Marine. Marine is just an ultimate WebAssembly runtime for backends. It implements interface types with a shared nothing linked scheme. And it fully supports Rust. It provides Marine SDK to help with like interfaces and so on. It's just how it's called? Macro. It's just a macro. And you can pass structures, vectors, objects, and such stuff, everything except enum types through the API of the service. There is a testing support for WebAssembly compiled modules, also provided by Marine Tests. There is a REPL, so you can test and run and try your services and modules in the console. And we have some modules compiled to WebAssembly with the help of Marine, which you can just take and reuse. For example, we have a SQLite that's very useful for service databases. We have an IPFS adapter to access and to call IPFS functions. We have curl that gives you an ability to execute almost anything over HTTP from the Fluence Node from the service. So they are also around. Another specific part of the Fluence Node implementation is the distributed event loops. It's like a cron-like Air means Aqua scripts. We call it scheduled scripts. So you can take an Aqua function, compile it, and upload as a script to a Fluence Node, and to specify an execution schedule, like every 1 minute, for example. And it means that you can wake up your services periodically and do something with it. For example, it's very useful to perform data replication or synchronization with these scheduled scripts. Or actually, it's used widely to make sub-protocols. For example, if you think about Raft or, I don't know, PubSub or DHT, probably you will need something to run periodically, and we have it implemented. So now we covered enough to speak about the built-in services, built-in libraries, and sub-protocols which come with the Fluence Network out of the box.
Sorry to interrupt, Dmitry. I just wondered if anyone maybe have some questions, because a lot of stuff has been covered. So if anyone has questions, please ask. But if not, that's totally okay. So Dmitry, you just covered two kinds of Fluence peers, right?
Right. Both of them are peers, but they are different. One kind of the peer of peers is implemented with TypeScript, and another kind is implemented with Rust. Rust peers are much more powerful, but TypeScript peers can run from the web browser, and they are much easier to handle. Like, you just need to know TypeScript to do everything in the Fluence Network, thanks to the TypeScript peers.
Yeah, so if you even don't know Rust, you can right now go and write your own TypeScript or JavaScript peer, run it in the browser, and connect several browsers into a peer-to-peer network and do some stuff, write your application with it and provide different APIs and people already do that. So that just works.
Yep, you can, like Aqua, the language is quite affordable, and it's simple. It's simple because it's not Turing complete, by the way, and it's very domain specific. So it's quite straightforward to use it for TypeScript developers without touching Rust. But if just connecting the browsers is not enough, we have some defaults provided as services. Eddie?
I have a quick question. Let's say if you have like a custom browser, or running some type of browser that you may have some different, I guess you could say, different engines that you can use. Can you still use those browsers, you know, with the built-in services and some of the parts of the Aqua libraries?
Aqua libraries are executed with the help of AquaVM, which runs on any browser that supports WebAssembly. It's literally everything.
So
you can.
I'm using Wasm. I can do that.
Yeah.
I'm using like that. Yeah. Okay.
Yeah. So the browsers are they just have the same capabilities in terms of Aqua as the Rust nodes, and in terms of Aqua language and in terms of the Fluence protocol, you don't notice the difference between the peer implementations, and actually this three layers system design of the Fluence Peer is more or less straightforward to implement in other languages, because we have many lib2p implementations, we have WebAssembly support in many environments, and the services support could be different, and the most you can attach the most suitable one for your favorite language.
Okay. Yeah. Thanks.
We have a few questions in the chat. I can read them. So the first one is, you can use TypeScript for writing peer on browser. So where Aqua is used? Why do you need Aqua if you can use TypeScript?
Yeah, that's a wonderful question. Why do we need Aqua at all? So the special thing that we want to have is distributed like peer-to-peer computations. We want to enable these distributed workflows in permissionless networks. So this means that we have two different parts. I will open this slide again. We have a workflow coordination part, and we have computation part. So you can use any language, actually, if you can divide these two parts. And at first hand, we implemented the low-level language for orchestration, like for coordination and orchestration on the network. And we were trying to make it as flexible as we can to make it possible to implement, I don't know, Raft and Kademlia and such algorithms, which are pretty complex. So we don't want to be too strict and too limiting with no reason. And we want to add enough security, like circuit breakers, amplification attack protection, signatures checking, and such stuff. And this means that before we think about how to compile, for example, TypeScript to something executable on the network as a whole, we need to understand the domain very deeply and understand the contracts and the constraints that this domain introduces. And we study this in Aqua in the intermediary representation in AIR. So we have very simple instructions here, like sequential execution. Do the first one and then the second. Then we realized that it's hard to work with, and we decided to make a DSL that follows all the constraints and limitations and possibilities and capabilities and contracts of this low-level, very like rocket science kind of stuff in an affordable way. Affordable, what do I mean? I mean that we could have made, and we tried, we implemented the builder library in Typescript. But in this case, it means that you need to know and use Typescript, even if you're a C developer or a Rust developer or, I don't know, PHP developer. But why? Why Typescript? Why to limit with Typescript? We were able to implement the same with Rust, but there are some problems. One problem is that if you try to compile arbitrary code to this kind of asynchronous flow, you need to split it in the with the asynchronous boundaries, and it means that you need to have some specific semantics. For example, here we have on semantic. You need to explain where exactly you want to go after the asynchronous boundary. But Rust doesn't help with it. It helps with lifetimes, with different data types and so on, but not with distributed flows. So finally, we decided that the best DSL that we can implement and which is accessible and useful for the broader developer community is the specific language that will help solve this particular problem of describing distributed systems, programming distributed systems and peer-to-peer flows. But finally, if anyone wants to implement, I don't know, Rust library or TypeScript or anything else that can be divided, that will compile the code into computations in terms of services or functions or don't know what, and workflow orchestration in terms of PyCalculus, just go ahead. I think it's good and it's absolutely possible.
Yeah, thanks for awesome answer. Let me add a little bit to it. So in short, you can use TypeScript to define your logic on a single peer, but for anything that involves peer-to-peer network interaction, you will better use Aqua because it provides different primitives for routing and forwarding messages. And also, as Dmitry said, Aqua provides different security guarantees because it's not Turing complete and because it's domain specific and it tracks the signatures of calls and stuff like that. So for anything that involves peer-to-peer interaction, Aqua is the best. So it's like a kind of orchestration language which you can use to like compose different services, different peers, execute different functions on those peers, gather the data, then forward it to some other place, maybe send different events to your users or compute like a mean average of different prices from different oracles and compose all that to a single value and send back to your user, to your application, stuff like that. That's where Aqua shines. But when you want to define like the logic, like show this button or go to some website and download something, you better use Rust or TypeScript, whichever you know best. So that's kind of the division between Aqua and different languages.
Thank you, Alexei. By the way, this event is the very first one, and the goal is just to show what exists. The second event will be dedicated to Aqua language, and I will try to cover more like contracts, constraints, possibilities, capabilities, limitations, and such stuff of Aqua next time in 2 weeks. So let's continue with our brief, in-depth overview.
Yeah, there are a few more questions in the chat. I think we will cover them later, just to continue with the main flow.
So the main way to augment the capabilities of the Fluence network is to provide some services and Aqua bindings for these services and Aqua libraries to work with these services. And all of this together forms a reusable sub protocols on top of Fluence. This holds both for the default ones, and if you think about making an application on top of Fluence, actually it becomes a kind of a sub protocol written in this form. But about the main, the default node distro. Every node or even every peer in the Fluence network is expected to host certain services. And the whole set of these services form the main and the default Fluence protocol. We call these services built-in services because they are built into the node. There are some special ones which helps with like service deployment, getting the time and so on. You can read about this in documentation, and I will mention DHT, IPFS, and TrustGraph built-in services on the Fluence network. So first of all, Aqua DHT. The purpose of Aqua DHT is routing. It helps to locate the peer, the path to the peer, and the service on this peer to call to solve some certain problem. So, for example, you can do publisher subscriber using this, or you can do broadcasts, or you can do chat room, or you can do just multi-client setup when you have multiple devices and want to receive notifications to all. But initially, it starts with creating your own key on the Aqua DHT. And then you or maybe other peers may add records that points to actual runnable code, which includes peer ID, service ID, and relay ID. Service ID and the relay ID are optional, so you may just add the peer ID to the DHT and then route to it by the key. That's about routing and Aqua DHT. Then we have AquaIPFS. It adds, it like serves two purposes. It adds compute to IPFS network, and it adds file management to the Fluence network. This is the example of AquaIPFS usage, where we deploy the service from the WebAssembly module, which is stored on IPFS. So we download it by CID from some IPFS node, then move it to modules, then create the service, and it's runnable. So you can use it, and it's available by default out of the box. The third one is TrustGraph. It's a decentralized public infrastructure native to the Fluence network. It's very powerful and it's used to manage priorities and prioritize connections to protect from spam. You can create subnetworks with the help of TrustGraph and ensure that your subnetwork is your peers are connected with each other, or that you and some other peers like of some technology that you want to use are also connected directly, and you don't need to leave the global network to ensure that connections in your cluster exist. And also it can be used for authorization, just to check the permissions to access some service or resource. In the future, we are planning to integrate it with the DID and VC specs and to enable a service discovery with the help of like Web of Trust concepts using TrustGraph as the underlying cryptography DPKI layer. So that was all about the moving parts, and a couple more slides about the developer experience and community. So we have a lot of tools and means to work with Fluence Network and to make peer-to-peer applications fast and like to debug them and so on. The main parts are Aqua and Marine. With Aqua, you can compile, run, and provision Aqua scripts, and it's also used to deploy the services. The main purpose is to program distributed networks. It's like with Aqua, you can create programmable networks. We have Marine with all the tool set to develop, debug, and run backend WebAssembly services. You can compile Rust and C code into linked, portable, and reusable WebAssembly modules. Also, we have Aqua libraries that you can reuse, and WebAssembly modules and services, which are also available on the network and as a source code. We have VS Code support for Aqua, the language plugin, and the dev container to speed up onboarding into Aqua development. We have documentation to check out documentation and the quick starts and so on. Go to fluence.dev. And we have a dashboard that can be used both to monitor and navigate the running network, which we also have, or the private deployment, or your private node during the development process. So it's deployed on dash.fluence.dev, and by the way, it's also implemented in Aqua. This is the very first community call, but let's keep in touch with all the means possible. We have a Discord. To join Discord, go to fluence.chat. We have a Telegram chat for developers. It's fluence_dev. All the code is open source in the Fluence Labs GitHub organization. We are hiring some. Like you can take a look on our offerings on fluence.network/join HTML. We sponsor hackathons. Currently it's Gitcoin and ETH Online. And on the following community calls, we will invite some projects or maybe even you to present what you're building on Fluence, what's your experience, and so on. So we want to grow the community with your help. We have a plan for community calls. So today it was just an overview of what exists, and that's all. And on the following community calls, on the following events, we'll focus on different technologies. We will start with Aqua, continue with Marine. Then we will go in depth into Aqua virtual machine and this calculus, CRDT implementations. Then we will speak about Fluence for JavaScript and Typescript developers and how to make the best experience with JavaScript. And then we are planning to cover Aqua DHT for routing and for solving the default peer location problems with Fluence with the help of Aqua DHT. And hopefully then we will continue with the TrustGraph and security management in Fluence. Thank you. That was all my slides.
Awesome. And we have a lot of questions in the chat. I think we can answer all of them. What do you think? Sounds
I don't
fun?
know. We
Let's
have
try.
a big part of the Fluence team here, so anyone can answer probably. Let's try.
So the first unanswered question we have is, how do you protect from spam or malicious code sent to be executed on other peers? I guess that was partly answered by presenting TrustGraph, but I think we can elaborate on that. Right.
Yeah, we can. It's a multi-layered problem. We have WebAssembly code running on the Fluence nodes, and the Fluence nodes should somehow be protected from the excess code sent by the network users. We have effects, which also should be secure somehow. We have the Aqua code that can be which can suffer from the man in the middle attacks, or that could force peers to make more and more calls and to lead to augmentation attack, or we can have the Sybil attack. So there are many attack surfaces, and speaking short, we provide isolation on every part and accounting on for every algorithm that's here. So we have the signatures on the AquaVM side to ensure that the data is not changed on the way the particle flows. We have circuit breaker that limits the maximum number of hops that the particle can do on the network. We have isolated pure modules sandboxed without system interface access for the WebAssembly modules. So it's just such a huge topic, by the way. I cannot just answer like we do it this way. A lot of approach.
We should have a topic. We should have a dedicated call on this topic, I think.
Yeah, we will have it. But actually, I think that we will, at first, we will cover parts of this problem, like part by part. For example, in the marine, when we will speak about marine, we will speak about isolation, memory isolation, WASI interfaces, and so on, and the particle file vault and like something like that. How we make it impossible to exit, to escape the sandbox. When we will speak about AquaVM, well, like we will cover it step by step.
Okay, awesome. So the next question is, what is actually AquaVM? Is it WebAssembly plus services for intercommunication with browser? I think Mike wants to answer that question.
Yes. Hi, guys. Sorry, I'm without camera today. So regarding this question, AquaVM and services are two different things. And AquaVM could call services, and services now could be located only on nodes, not on clients. By clients, I mean browser. But AquaVM could be run both on nodes and browser. And in future, probably we could also allow services to run also on clients. Like regarding the second part of the question, intercommunication with browser. So it means that like on, as I already said, AquaVM could call services without some helps of Marine on Node. But on browsers, like it's not strictly so like in intercommunication, but probably it's like just particle handling through our JavaScript CDK. So that's it. Hope I answered your question. If not, please ask more.
Okay, please. AquaVM works based on WebAssembly.
Yes, exactly. So AquaVM is a code that's written on Rust. So actually, it's about 15,000 lines of code. It's written Rust and then it compiled to WebAssembly and run both on client and on Node. And like on a client, it's run as with help of WASM engine. So it's just yes, a WebAssembly module that runs through some like general browser virtual machines like V8 for Chrome and the SpiderMonkey for Firefox and so on. And on Node, it runs through our runtime that Dmitry said that called Marine.
Okay, thank you.
Thank you, Tom, for the question.
Okay, thank you, Mike. So the next question, I think I'm going to take it. Who chooses the peers to execute the code on? So Aqua gives you ability to lay out the routing that you want to have. You have to find peers on your own. Like currently we have DevNet and testnet, and you can use any peer for routing there. Every peer will just serve you as you ask. There is no there are no rules. You just do what you want. So you just write in Aqua, go to this peer, then to this peer, execute this service on that peer, execute this service on that peer, and it just works. In the future, it will be a little bit more complex. You will have to find relays, you will have to add them to TrustGraph and stuff like that. But currently, you just specify the routing, the subnetworks, the travel path for particles that you want, and that's it. It just works.
Well, may I add one addition? Finally, the code is executed somewhere on certain peers. So between you and the code execution somewhere, there is the process that we call routing. And it means that you map the job that you have to some peers which are capable to handle this job. So in Aqua, you don't have to specify all the IDs of all the peers in advance. You can ask the network to help you to find the peers if there is a way that the network can help you. For example, you can have a topic, a service, a DHT key, and you can ask all the nodes which has some service to join to promote themselves to this DHT key. And then you just write resolve this key, and on the peers which are resolved, call this code. Or you can do it another way with some cryptography checking, or you can store the list of the peers on blockchain and provide the access to this blockchain with the Oracle, which could also run on Fluence. That depends on the problem. But like finally, in Aqua, you will have the information about where exactly the code will be running. And now it's either just write it or use something like Aqua DHT like to provide this mapping for you.
Yeah, and one more thing to add is that while you want to call services, if you want to call some code to execute, it should be a Fluence service, but it could be just an adapter to an external service. So you can integrate with Ethereum node, or you can integrate with some external service. You can, for example, make some hoster host some application that you care about, some daemon, for example, IPFS. We have IPFS integrated to all of the Fluence nodes, and we have just a small thin WebAssembly layer between Fluence and IPFS, and this allows you to call IPFS through Fluence. What I want to say is that you don't have to migrate your services or your daemons to Fluence to make it work. You can just provide a thin and very, very simple adapter service to call external services. Yep. And regarding the question, is there a catalog of some sort of peers that you have to follow? You can say that there is a catalog. It's called Kademlia. So it's a DHT network. It's a peer-to-peer network where peers announce to each other that they know other peers and how to make a route to them. So that's kind of distributed, decentralized catalog of all the peers in the network. Hope I answered your question. Okay, so the next question is about Ethereum integration. It's basically asks how Ethereum is integrated or used. Bernard, can you?
Sure. It's the integration is basically it's ad hoc right now, but we got a pattern for it, and porting some of the Web3 libraries is on our list. So we've done it through JSON RPC right now, because one of the really cool things with the particularly, so if you go through Rust, you can use curl to do your JSON RPC calls. If you use the client-based approach with JavaScript, you can just import one of the Web3 libraries. But from a purely distributed perspective, there is no library available right now. However, we have 2 hackathons going on right now that actually rewards you of working on this very particular topic. We get the Gitcoin GR11 hackathon going on right now, and we have the ETH Global hackathon starting this week. So if you want to turn your excitement into reward and some actual code, this is a great opportunity, and we'd be super excited to support you in that, or anybody who works on that. And that goes for other integrations as well. So that's all I got to say about this right now.
Thank you. So we have one last question. I think we're not going to address that in full here. It's asking what additional literature can I read about the topics we covered. Let's talk about that on Discord. You can follow our documentation and ask anything you don't understand, or just start an open question in Discord, and we will talk about literature and papers and stuff.
Yeah, but the main entry point is fluence.dev. Yeah. So, Alexei, am I right that we answered everything that that we have right now?
Yep, I don't see any more questions. So, word to Anna, I guess, or maybe not.
I think, hi everyone. I think everything has been covered for this event. If you have questions about the hackathons or about this that we are running right now, please just reach out. We are everywhere in Discord, in Telegrams, in email. You can also book a call with the team for the support for the hackathons. And we started the community wiki, so we will document everything what's been happening at the calls. So we will have recording of the calls. Yeah, and thank you everyone for joining today.
Thank you, everyone. Excited to have these calls, and please subscribe to updates somewhere, anywhere, and join next calls as well. Okay.
Thanks, everyone. Bye.
Thank you.
Bye.
Bye.